everyone. This is Alex, and it's a pleasure to meet all of you. A little bit about myself. I'm going into my last year as a math major at UC Berkeley. I study pure math with a great interest in discrete math, especially combinatorics, in things like random walks, where I actually have an ongoing research project. And those of you who haven't heard the term of random walk is basically like if you flip a coin over and over again and you picture yourself as walking on the plane, basically, where you flip ahead, you go up by one, and you flip by tails, you go down by one. And I'm interested in studying a lot of the properties of those paths, but that's neither here nor there. As you might know, I'm thinking of branching out later into other videos, so you might see some of that. But anyway, I've done math contests since the beginning of middle school in the math count series, the AMC8 and the 10 and 12, and the AIME, and even the Putnam Exam, and also several other contests run by colleges across the country. I've even made a few math contests of my own, as you can check out. I might put a link in the description or something. So in this video, we'll be briefly introducing what a proof is and why it's important. And then in our next video, we'll start getting into some other types of proofs that are other than a direct proof. So without further ado, let's get straight into it. So why do we really study math? Well, we want to know the truth of the universe. It sounds simple enough, right? But is math just a bunch of disjoint facts? Well, I hardly think so, because it's more interesting to want to know the motivation behind them. Like, that's all well and good, but how would I have ever thought of that by myself? Or, okay, that's cool. Now, what can I do with this? And how can I generalize this to other things? But even more important than that is the art of proof, because we need to be able to show beyond any shadow of a doubt that some statement that we're trying to prove is in fact true, and some of its logical implications in a way that can really only be described as, well, mechanical and without appealing to any kind of like logical fallacy or common sense or, oh, come on, that's good enough, right? We have to be really precise and methodical. So you want to think of it as like being a prosecutor in a courtroom, but with even less room for like hand waving and just common sense, which would really be none in an airtight proof, right? Now, if this sounds intimidating, don't worry. All this really means is we have to be logical in the way we work in math. And this means going through a sequence of steps from which every step follows from the last without any gaps in reasoning. When we speak of a proof, right, we're really speaking of that sequence of steps. How do I get from point A, the premises we have, to point B, the statement that we actually want to prove? And much like a real journey, there's almost always several ways to do it. Some are like more of a scenic route than others, but they all should be equally correct, right? And if you're the type who's just interested in doing the straight shot without any detours, well, what better place to start than with a direct proof? So, for example, let's start by trying to prove that when x is a positive integer, x squared always leaves a remainder of 0 or 1 when you divide it by 4. So maybe let's write it like this, right? So this is a pretty typical form of a statement that you might be asked to prove. So where do we even really begin? This is a statement that may seem pretty plausible if you just try out a few values of x, like I don't know, 9 squared, right? That's 81. So you can see that leaves a remainder of 1 when you divide by 4, or 12, or 3, or 59. All of these seem to produce results that don't contradict what we want to prove. You can check that last one on your own. But that's just it. That's a problem. Just because we don't have any evidence to the contrary, that's not enough to actually prove the statement definitively. We need to show that it's actually true, not just that it doesn't seem to be false. Because in math, seem isn't good enough. We need definitive answers. So we might ask ourselves, what kind of possibilities do we have for x? Well, it's an integer, right? This is the important part of the problem. X can't just be any number or any real number. X has to be specifically a positive integer. It's a positive integer, but that doesn't really matter to us right now. I guess that distinction doesn't really matter. It can also be a negative integer. We'll keep it positive just to keep things simple. Right? So it's either even or odd, right? And that means, well, its remainder when divided by 2 is 0 or 1. So I'm just going to put up that for now, right? And so what does that mean for how it can be represented as some integer quantity? So we're going to go ahead and move to a blank slide where I have more room to write stuff down. If we let, say, I don't know, k be some random arbitrary integer, then if x is even, it's equal to 2 times that k. And if x is odd, it's similarly 2k plus 1 for some integer k, right? Because those are the definitions of even and odd numbers. And what that integer k happens to be is irrelevant, right? Because, for instance, 7 equals 2 times 3 plus 1, and 16 is equal to 2 times 8. That integer k always exists is the important part. So when we square both of these guys, what do we get? Right, in the x is even case, we get 2x squared, that's 4x squared, right? And the x is odd case, 2x plus 1 squared, which is the only other case we have. Then we get, well, let's see, 2x plus 1 squared. Remember the FOIL method, just as a quick refresher in case. 2x plus 1 times 2x plus 1. First, you go first, right? 2x times 2x, that's 4x squared. Outer, 2x times this guy, this outer guy, this 1, 2x, and then inner, which is also 2x, the 1 and the 2x. And finally, last, well, that's just 1 times 1, that's just 1. You have 4x squared plus 4x plus 1, right? And now, what do we notice? We notice that the 4x squared, well, it's definitely a multiple of 4, right? Because you can write it as 4 times x squared. And of course, x squared is an integer whenever x is, because you're multiplying an integer by itself. That's what x squared means. Great. Now we're really onto something. We're actually almost done, because what this other case just gave us, this guy, well, what that is, that's actually 4 times the quantity x squared plus x in parentheses, plus that extra 1 at the end. And that 1 is what matters to us, because it's 4 times something. We don't really care about what that something is, plus 1. And that fits the form of an odd number, if you remember 2k plus 1 up here, because that's the definition of an odd number. So we've actually covered all possible cases. And what we can actually say is something even more significant than what the problem asked us, because not only are the possible remainders, when you divide a perfect square by 4, 0 or 1, we've also just shown, so I'm going to pull up the solution right here. We've also shown more specifically that the square of an even integer is a multiple of 4, which may seem obvious, and the square of an odd integer is 1 more than a multiple of 4, which may seem less obvious, considering that some odd numbers leave a remainder of 1 upon division by 4, but others leave a remainder of 3 upon division by 4, like 3, 7, 11, and those two, when you square those, you also get 1 mod 4, even though they have different remainders when you divide by 4. So that's that for that example. In this video, we've taken a look at the direct method of proof and some of the basics of proof writing, but so far we're just scratching the surface, right? For a deeper dive into how to write a proof, feel free to check out the other videos in this series. And in the next couple of videos, we'll be going into some of the more general proof methods like induction and contradiction. And then we'll also go through several more examples, maybe even going into parts of some real contest examples. But until then, I'll leave you with a couple of exercises up here. Exercise 1 and 2, you can just do on your own time if you want. But until then, I look forward to seeing you next time. Take care and have a good one, everybody.